So we talked about the energy level split within atoms and how do we use principle four different quantum numbers to represent the electrons in different orbitals, the other class. So sum things up a little bit here. The four quantum numbers that we introduced so far are principal quantum numbers, also known as the shell number. So first shell, second shell, third shell, fourth shell. Okay, angular momentum quantum numbers are the subshells, represents the subshells. Okay, that's the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, and then magnetic quantum number represents each of the degenerate orbitals within a subshell. Okay, and the spin quantum number represents the up to 2 electrons within each individual degenerate orbital that you can put in. So altogether, these four quantum numbers determine that there's no 2 electrons within the same atom would have the same exact set of quantum numbers. Because even if they have 3 of the same with principal quantum number, angular momentum quantum number, and magnetic quantum number, they ended up in the same degenerate orbital, they would have different spin quantum number, either plus 1/2 or negative 1/2. So with all four quantum numbers, we essentially built a structure, okay, to identify every single electron within a given atom, regardless of how many electrons you would have in there. Okay, so in a way, I have a metaphor maybe can help you understand how this works a little bit. In a way, you can view this four quantum number system, okay, just like a university's dorm system. Okay, now, what do you mean? Well, the principal quantum number tells you which building you're in. Okay, the angular momentum quantum number tells you within the building which floor you're going to be in. The magnetic quantum number tells you on a given floor which room you're going to be in. And then the spin quantum number tells you within each dorm room, let's say we put 2 beds or 2 students there, okay, spin quantum number tells you the 2 people that you put into a dorm room, who is who. Now, in that sense, each of these little dashes, okay, is a room in that dorm system. Okay, the first building have 1 floor, and that 1 floor only has 1 room. The second building has 2 floors. First floor have 1 room, second floor have 3 rooms. The third building have 3 floors, 1 room, 3 room, 5 room. The fourth building have 4 floors, 1 room, 3 room, 5 room, 7 room. And the building can go on and on and on, regardless of how many students you're going to be putting in there. Okay, and each student is different, and you can differentiate them by which building they're in, which room they're in, which floor they're in, which dorm room they're in, and which bed they use in that dorm room. And no 2 students will be assigned the same bed. Okay, everybody has their own individual bed, And that bed is building, floor, room, and within the room. Yeah. So, all right, now, and this structure also gave us an easy way, okay, to figure out how many electrons you can accommodate, okay, within each shell, each subshell, so on and so forth. Okay, so what kind of question are you going, conceptual question are you going to ask us now that we talk about all these conceptual stuff? So let me give you a couple examples. Now, what is the maximum number of electrons that can be placed in 3D orbital? What about the sixth shell? Okay. All right, so 3D orbital, how many electrons can you have? Okay, so let's look at our scheme. 3D is right here. Okay, now, and all the d orbitals in our scheme, okay, where L equal to 2, so it's d orbital L equal to 2. Okay, and L equal to 2, your ML should equal to, the limitation is from -2, -1, 0, +1, +2. 5 values, 5 orbitals. So a 3D subshell, okay, will have 5 individual orbitals. And each orbital can take 2 electrons at most, so 5 times 2, so 10 electron max in 3D. All right, what about 6th shell? Well, 6th shell would have a bunch of subshells. Okay, and based on what we see here, first shell have 1 subshell, second shell have 2 subshells, third shell have 3 subshells, so you can imagine, okay, 6th shell would have 6 subshells. Okay, and each subshell would have, let's see, let's say we have s orbital. Okay, any s orbital would have subshell, number of orbitals, and number of electrons, 2. P orbital would have 3, and that's double that, 6 electrons. D, 5 orbitals, 10 electrons. F, 7 orbitals, 14 electrons. G, that's the next one, 9 orbitals, 18 electrons. And beyond G, we actually don't have letter designation for the subshell anymore, because so far with all the elements on the periodic table that we know, we don't have an element that it could even get into G orbital, let alone the orbital, the G subshell, let alone the subshell after that. So it's going to take us quite a while before we get there. And so whatever that is, be 11 and 22. So now, if you have first shell, okay, your subshell is going to be 1s, and you're going to have number of electrons, total of 2. second shell, you're going to have 2s, 2p, and the total electrons would be 2 plus 8. Third shell, 3s, 3p, 3d. 2 plus 6, sorry, earlier. That's 8. So 2 plus 6 plus 10. Fourth shell, 4s, 4p, 4d, 4f, 2 plus 6 plus 10 plus 14. Now, fifths, 5s, 5p, 5d, 5f, 5g, 2 plus 6 plus 10 plus 14 plus 18. And then, of course, 6, 6s, 6p, 6d, 6f, 6g, 6, whatever, let's call it edge. 2 plus 6 plus 10 plus 14 plus 18 plus 22. And that total should equal to 72 maximum electrons. Okay, and now, does that mean if you ask me about shell number 12, then I need to do 2 plus 6 and all the way up to go to what? 23 orbitals or 46 electrons? No, you don't have to. We actually figured out an easy way to do that. Okay, and that is for the nth shell. Okay, maximum number of electrons should equal to 2n squared. First shell, we have 2 electrons. Second shell, we have 2 plus 6, 8 electrons. Third shell, we have 2 plus 6 plus 10, 18 electrons. 32, 50, and 72. And you can look at each of them. 2 times 1 squared is 2, 2 times 2 squared, 2 times 4 is 8, 2 times 3 squared, 2 times 9 is 18, 2 times 4 squared, 2 times 16 is 22, 2 times 5 squares, 2 times 25 is 50, and 2 times 6 squared, 2 times 36 is 72. So maximum number in an nth shell, okay, is 2n squared. Something that you can actually calculate pretty easily if you're asked that. And now, this is the number of electrons that, or a subshell, a certain shell could accommodate. Okay, what other questions can you ask me about in this conceptual stuff? Well, let's see. One more example. Which of the following sets of quantum number contains mistakes? Okay, so 1, let's say n equal to 0, L equal to 0, ML equal to 0, and ms equal to plus 1/2. Number 2, n equal to 2, L equal to 2, ML equal to -1, ms equal to -1/2. Number 3, n n equal to 6, L equal to 0, ml equal to plus 1, ms equal to plus 1 half. Number 4, n equal to 3, L equal to 2, ml equal to 0, ms equal to 0. Okay, so let's see. Now, remember, each quantum number is having its limitations. Okay, the principal quantum number starts with 1 because it's the shell number, first shell, second shell, so on and so forth. So right there, you see your mistake. Your n would never equal to 0. Okay. Yeah. All right. Second set, nothing with n equal to 2. Okay, n could equal to 1 all the way up to infinity. Okay, but L have its limitation, and that limitation is by n. L is from 0 all the way up to n minus 1. So if your n equal to 2, your L could be 0, your L could be 1, and there's no way that your L equal to 2. Okay, L couldn't equal to n. No, ML is negative 1 is fine, it's in the range. MS is negative 1 half, that's just whatever you want it to be. No. All right, number 3, n equal to 6, that's okay, 6 shell. L equal to 0. Okay, L equal to 0 means S subshell. Your 6 shell could have a subshell, S subshell, 6S orbital. Okay, that's fine. Now, ML is limited by L. If your L equal to, whatever L is, your ML is from negative L all the way up to positive L. If your L equal to 0, your ML can have only one value, which is 0. And what does that mean? That means any of your s orbitals should only have one degenerate orbitals. Okay, no further splits. No. And this one here says ML equal to plus 1. Your ML can't be plus 1 if your L equal to 0. Okay. Number 4, n is fine with 3, L equal to 2, ML equal to 0. All matches. No, L is n minus 1, that's okay. ML from negative L all the way up to 0, and then all the way up to positive L, that's fine. But MS have only 2 values, positive 1 half or negative 1 half. And it obviously couldn't equal to 0, so that one would be containing a mistake as well. No. All right, so this is how orbitals are defined and designated, and how we understand the structure of it. Okay, and now once you have that structure in place, now we can start to try to place electrons into these orbitals, because like we said before, now hydrogen have only 1 electron. Okay, but we're not only dealing with hydrogen in chemistry. We have all these other elements on the periodic table. Some contains over 100 electrons. Okay, how does these electrons behave within the atom is a very, very important aspect. Okay, and relates a lot to the element's chemistry. And that's why we need to know how they're distributed, how they behave within a atom. No, but before we start to put all these electrons into these orbitals, okay, now I want to introduce something else, and that is, change color. The shape of the orbitals. Now, because orbital is kind of a very abstract concept. Okay. And whenever you think about it, you feel like, okay, do what? You put them in energy scheme, like, is it a place your electron would be staying? Yeah. Or what exactly is an orbital? Okay, now, and now, does electrons with different energy or in different orbitals, okay, stay in different places inside atom? Okay, well, the answer to that is, well, yes and no, I guess. No. The reason I'm answering yes is that it's because, well, each different orbital, okay, definitely represents electrons with different energy, and if they have different energy, okay, they kind of behave differently. They kind of do show up in different places within the atom. Okay, but the reason I say no is that it's not like you can put some of these higher energy electrons in on one side of the nucleus, some of these lower energy orbitals into another side of the nucleus. No, that's not how it works. Okay, each orbital, okay, is kind of, these orbitals, they're kind of a collection of possible positions within an atom that the electron can be located. Okay, now, and if you're not quite understand, if you don't quite understand what I'm talking about, let's start from the simplest orbital. Okay, so s orbital, okay, or s subshells, however you want to call it. Okay, and we say the s orbital is having a spherical shape. What do you mean? I'm saying, okay, if we put space into 3 axis, that's our common 3-dimensional space, okay, and right in the point of origin of our space, let's say it's our nucleus, okay, now, a s orbital would take a round ball shape. Okay, hold on. What do you mean by this? Now, what I mean is like if you put a electron, locate a electron in our structure earlier, and you say I have this one electron or 2 electrons on this one s orbital. Okay, now then I'm telling you that your orbital will be in one of these positions, okay, in that ball, okay. Or you can say, if you can somehow take pictures, okay, of your electrons in that orbital, okay, and if you combine, okay, billions of billions of billions of those pictures, now overlapping them, this is what you're going to see. Okay, you're going to see that electron could be here, it 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 could be all over the place. Okay, but what you won't see is your electron won't be there. Okay, your electron won't be here. Okay, your electrons in that s orbital are all within this region. As of where in the ball your electrons could show up, we don't know. Okay, and we can't really say, well, it's going to be at this particular position. We have no idea. Electrons are too small and too fast. But we know that if it's in the s orbital, it's here in this ball. Okay, or in this ball-shaped space. All right, now, and if you can understand that, then you shouldn't have too much problem understand that when we're talking about p orbital. Okay, we say p orbitals have a dumbbell shape. Okay, what's a dumbbell shape? So let's do our three-dimensional x, y, and z axis. Okay. Yeah. Okay. Your p orbital, okay, would be a dumbbell shape centered on one of the axes. And if you're wondering which axis, well, we're in a three-dimensional space, right? We have three different axes. Remember how many degenerate orbital each p orbital has? 3. Well, each of those 3 p orbitals, okay, will be centered around one of the axes. And again, right in the middle of it, in the center, in the point of origin, that's your nucleus. Okay, but for this p orbital, for this one p orbital, your electron, if placed in that p orbital, it would only show up in the region that the red color dumbbell is occupying. It won't be anywhere else. Okay, there will be the same orbital, same shape, same size, centered around the z orbital. There would be another one centered around the y orbital. Okay, all 3 of them 90 degrees to each other. Yeah. So that's the p orbital. Okay, and d orbitals are actually a little bit more complicated. Okay, now. And that's why I'm asking you to remember the s orbital shape and understand the s orbital shape. I am asking you to understand and remember now p orbital shape. Okay, I'm not requiring you to do that for the d orbital because d orbital is actually a little bit more complicated. Yeah. I'm only going to draw one of them. So x, y, and z. So d orbital kind of look like this. Well, first it's a dumbbell centered on the x orbital, on the x-axis. And if you look at this, you go, what's the difference between s orbital and p orbital? No, this is not the complete. What's the difference between p orbital and d orbital? This is not the complete d orbital yet. This is one of the d orbitals. What do you mean? Well, what I mean is that the shape of a d orbital looks like a double dumbbell. No. Okay, and double dumbbell that's 90 degrees to each other. Okay, form this clover type of shape. Okay, on your x-axis and y-axis. Okay. And what about the other d orbitals? 3 other d orbitals out of the 5. This is 1, and you have 3 others that looks just like this clover type of cross dumbbell shape. Okay. but it's just pointing to different direction in space. Okay, and there's also another d orbital that's having a different shape. Okay, and that one would have the shape of one dumbbell circled by a donut ring on the waist of the dumbbell. Well, you don't have to memorize that. If you are interested, you can look into your textbook and find much better picture than I draw here. Okay, but the whole point here is for you to at least know your s orbital and your p orbital shape, and also understand, okay, each orbital essentially is a collection of positions, and for your electron in that orbital to show up at. Okay, and if you're wondering, okay, what about, you said s orbital are this spherical shape. What about 1s and 2s? Are there any difference between them? No, there are. The size of those spherical ball shape is going to be different. Okay, but they're all centered around the nucleus. And same thing for your p orbital, d orbital, or whatever. Okay, now, all right, so once we discuss the shape of orbitals, the next thing we're going to do here, okay, we're going to now discuss the electron configuration of a given element, and that is putting electrons into, so electron configuration of different atoms. Okay, and this is a process of distributing electrons into orbitals. All right, so how do we do that? Before we do that, okay, let's clear something up. Okay, now we actually have some rules to follow, and the set of rules that we use to distribute electrons, we call it the off-ball principle. And number one, now we have a few guidelines. Number one, fill electrons into the lowest energy level first. So when you're putting electrons in, okay, starting from your first electron all the way to your last electron, okay, you're putting your electrons in a lower energy level first, shell, subshell, whatever, okay, until you fill up the lower energy level. You don't go up to the higher energy level. Okay, number two, 2 electrons at most. In one orbital. Okay, this particular rule is also called the Pauli exclusion principle. Okay, and then number 3, now, electrons fill degenerate orbitals degenerate orbitals, if you remember, the orbitals within the same subshell, okay, with the same spin. The same spin, unpaired. First. And this individual rule is also called the Hund's rule. Okay, so what do you mean? And well, let's put this to work. Exactly how do we follow the rules here? All right, so let's get our scheme out first. If you remember, we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, so 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, so now let's put electrons into these orbitals and see how it works. Okay, now, and the first electron goes in here, but since we already determined that there's at most two electrons within a given orbital, okay, and those two are having opposite spin quantum numbers. How do we represent that? We're going to use upper arrow and lower arrow to represent electrons. Upper arrow means a positive spin, or you can say, now that's the electron with the +1/2 spin quantum number, and then the downward arrow, let's say it's a negative spin, or you can say this is the other electron, okay, or the electron with the spin quantum number of -1/2. Okay, so the order that we put in the electron are now going to be like this. Now, I'm going to put the first electron in, and then that's going to have to be on 1s because that's your lowest energy. Okay, and which one do you put, positive spin or negative spin? Doesn't matter. Let's say I put in positive spin. Okay. Okay, the only thing it matters is that this only promises that the next electron that you're going to put on the same orbital is going to have to be a negative spin. Okay, otherwise it's not going to work. Okay, otherwise you're going against, okay, the Pauli exclusion principle. Okay. Now, so what about the second electron? The second electron still you need to fill up the lower energy. 1s is the lowest energy, okay? Now, before you can go on to the next level. Okay, so that's 2 electron, 3 electron, 4 electron. Okay? And then your 5th electron is going on 2p. But first of all, where do I put it? The answer is don't matter. All 3 degenerate orbitals here in 3p are equivalent to each other. Your first electron can land anywhere, okay? Now, and let's say my first electron landed here, and let's say it has a negative spin, okay? Nobody says I can't, so I'm going to do that. No. All right, so now the question is, where is your electron number 6 gonna go? Now, can you go, let's say, use a different color. can you go here and pair it up with this negative spin red electron? Okay, the answer is obviously no. Okay, why? Because your Hans rule says your electrons will fill degenerate orbitals, and all three here are degenerate orbitals. Okay, the electrons are going to fill them, okay, with the same spin unpaired. Okay, that green electron is not the same spin. So how do I satisfy same spin unpaired? Well, easy. Next one, I'm going to put it here. Let's go back to our red pen. And the next one should be there. Okay. Well, now, what about your fourth electron? Well, your fourth electron can start anywhere, but it has to be a positive spin now. Okay. Fifth, sixth electron. Okay. Problem solved. Now, that used 10 electrons. Okay. And people are going, once we establish the rules, doing this is easy. Because I know you're going to do number 11, number 12, number 13, 14, 15, 16, 17, 18. Right? No problem. I got this. I can put them all in pretty easily. Okay. Now, based on the way that we did things here, you can see in our scheme. Okay, the next one would be the 3D orbital, which makes perfect sense. Well, you're gonna fill up the lower energy 3D orbital before you go on to the higher energy 4s orbital. Okay, and of course, people would say that the next one. Okay, I'm gonna put an electron there. Okay, now for the first 18 elements, okay, on your periodic table, your R scheme worked out perfectly. Okay, everything is what we expected. Okay, but when it gets to number 19, okay, we found that we got a little bit of problem. What do you mean? Oh, here's what I mean. Instead of having your next electron on the 3D orbital, people found that, that electron is on a 4s orbital? Why? Can you skip 3D orbital like that? No. Doesn't this go against the rule? You have to fill up lower energy level first before you go into a higher energy level. 3D should be lower than 4s, right? You can't skip 3D. Well, the reason the electrons skip 3D, and this is not a one-time coincidental type of occurrence. People ended up finding that, hell, for every element that has more than 19 electrons, seems like their 19th electron always fall onto the 4s orbital and skip 3D orbital. Okay, why? Well, that's when people goes in and start to listen, to start to calculate, start to trying to figure out why 3D orbital, okay, is being overlooked. Okay, and then they found, okay, number 19 is going to be here. Number 20 obviously is going to pair up. Okay. Number 21 somehow showed up on 3D instead of going one step further. Now we're kind of totally confused. What exactly happened? Now, why is this happening? And now that this does happen, does it completely destroy our rules? But it did work in all these previous ones, and actually for the later ones it works as well. Yeah. So, how should we explain this? And eventually people found a explanation. Okay, why does 4s show up, orbitals are filled before your 3D orbitals are filled? Okay, the answer is, well, this whole splitting into different energy levels thing is actually more complicated than we thought. And by people's measurement, and they eventually found out, okay, energy-wise, 4s is indeed lower than 3D. Okay? Then why? How do you explain it? Well, here's how we explain it. Remember all the splits that we do? We said that originally when we were learning hydrogen spectrum, it's this, first level, second level, third level, fourth level, right? And we said that they split. First one, no split. Second one, there's a split into two different energy levels, and later on we knew this is S&P, right? Third one, break down into three different energy levels. 1, 3, 5. Okay. And as I draw this, you can see, and I've been drawing this way since we, first deal with energy levels. Now, the higher you go, the smaller the energy gap is between you and your next energy level. Okay? And now this is going to be a dilemma, because we also know the higher we go, okay, the higher energy level we go, the more split we would end up having. So you would have a smaller and smaller gap between different energy levels, and you would have, as the energy level go up, you would have more and more splits. And the result of that is when your fourth shell, okay, break down into different subshells, the split actually becomes weird. Okay, your 4s orbital is indeed lower in energy than the 3d orbital. Your 4p is fine. Your 4d is okay. Your 4f is fine as well. Okay, it's just that your 4s falls actually between energy-wise your 3p and 3d. Okay, and now, as you can imagine, the higher you go, what if I go into the fifth shell? The gap is even smaller. And now you need to split into even more subshells, 5 subshells. And the result is all those 5 different subshells, they are going to overlap each other as well. Okay? Now, the higher you go, the more overlapping you have, the more messy it's going to be. Oh my God, you're saying that even with drawing the scheme, I still wouldn't be able to figure out which energy level to deal with first, which energy level to deal with later. No, that's not what I'm saying. I actually have a very easy way for you to know exactly which orbital you fill up first. Okay? And it goes like this. You can draw a triangular diagram on your paper. And it goes like this. First shell 1s, right? Second shell 2s, 2p. 3s, 3p, 3d. 4s, 4p, 4d, 4f. 5s, 5p, 5d, 5f, let's say 5g, 6s, 6p, 6d, 6f, 6g, and let's say 6h. And the list, of course, can go on and on. Now, okay, now, all right, so after you draw this triangular orbital list, okay, the next thing you should do is you want to draw an arrow crossing each of the orbital designation. And they're all 45 degrees to level and going down, okay? So, second one, third one, fourth one, fifth one, sixth one, if you have a 7s, okay, and this can go on and on. Now, why are you drawing all this? Well, this can easily tell you based on the order you're crossing off those orbitals. Okay, the first one you cross off is 1s. Then after that is 2s, and then after that is 2p, and then 3s, 3p. Now, you see the trend here. After 3p, do you go to 3d or do you go to 4s? Well, this arrow take you through 4s, okay, and 4s first, and then after 4s, okay, what do you got? You got 3d. Then 4p, 5s, and then 4f, 5d, 6p, whatever. Okay, so if you can do this diagram and draw the arrows, now you would never confuse which subshell is having higher energy in this process. Okay, so now that we understood all this, next thing we're gonna do in Chem 115 is to put all these elements that we know on the periodic table, okay, fit them into this scheme and determine what kind of electron configuration they have.